All right, so now we're going to take a look at example 3, and we're going to use the tabular method of proof. And in the tabular method of proof, a couple of things. One, I'm going to keep our trusty Venn diagram up for reference purposes. Also, I'm going to note that there is a assumed 1 out there. So what is 1? 1 is everything not in Q, P, or R, right? So that is 1, kind of the universal set, right? 1 is everything else that we have not been talking about. But based upon that, we are going to use the tabular method now to prove the same thing that we've proven a couple of times now. P minus Q and R minus Q is the same as P intersection, I said and before, I should have said intersection R minus Q. Right, those two sets are equivalent. Okay, so we're going to be looking at rows, and for each of these rows, we're going to be seeing if it's a member of P, it's a member of Q, or it's a member of R. So in this first row here, it is not a member of P, it is not a member of Q, and it is not a member of R. In the second row here, it is not a member of Q, or P, it's not a member of Q, but it is a member of R. From here on, I'm just going to draw N's and Y's to make it clearer. Now, if this is starting to look familiar, it should. It's a truth table. And just like we used truth tables before to prove things by enumerating all possibilities, we're going to do the same thing here to enumerate all possible combinations of set membership. It's the same concept. And just like before, so here we're going to have P minus Q, which means it is a member of P, it is not a member of Q. And if you want to get more setty about it, remember that's the same as saying P intersection Q complement, not Q. So because we know it must be a member of P, everywhere we see an N or a no for P, we can just write a no. We know that it is not that is not an expression of that set. Everywhere we have a P, now we need to look and see what is Q, right? Because this is P minus Q. So in this case, Q is an N, and in this case, Q is an N. So it does exist in both those cases. But down here, it is a member of Q, so it cannot be that particular row. Now we're going to look at R minus Q, which, just like before, means it is a member of R and it is not a member of Q, which means it is a member of the Q complement. And just like before, we can ignore anywhere where R is no. So let's just go down the list here. Everywhere we see a no for R, we can just mark that. And everywhere there's a yes for R, we need to look at Q. In this case, on row number 2, we see that it is not in Q, so that's a yes. Here we see it is in Q, so that's a no. Here it is not in Q, so that's a yes. And then here it is in Q, so that is a no. So for this column right here, we're essentially ANDing the two columns we just created together. So that's going to be no, 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 yes. No and no. Now let's calculate P intersection R. That is, when is an item a member of both P and R? So in our table, P and R have to be yes. No, 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 yes. No and yes. So now we're essentially going to take that column and remove any place where it is also in Q, which in this case is just that final row. And then here where it is yes, it will stay yes, because on that row it is not in Q. And the rest of these will be N. So essentially the columns that we're interested in are these two right here, because those correspond to our equations, and we see they are in fact equal. So that is proving through the tabular method that two sets are the same, which is exactly what we do with truth tables. So it's no different whatsoever. Incidentally, if you were interested, you could number in this last column here the section or the values in the Venn diagram that correspond to each of these rows. So if it's not in P, it's not in Q, it's not in R, well that corresponds to number 1, right? If it is in R but not in P or Q, well that corresponds to number 3. If it is in Q but not in P or R, that's 2. If it is in both Q and R, that is 5. I'm just going to fill the rest in. So all possibilities are enumerated by this table. And that proves that P minus Q intersection R minus Q is the same as P intersection R minus Q. So that's another tool in our arsenal, one that we've already had, that we've used before, but I'm just showing you that it still works with sets. If you have any questions, ask in the forum below.